Thank you very much. So I'm not sure how much I have to project for online versus in the back, so someone's going to be hearing me screaming. I run a biostats research group at Penn State University. The major focus of our work is on sequence count data analysis. So when I say sequence count data, what I'm really talking about is just a general catch-all term that talks about tabular count data from DNA sequencing, be it RNA-seq, single-cell or bulk, or 16S microbiome sequencing or tabular representations of metagenomics. Now, one thing that's common to all of these technologies is that the sequencing depth is essentially arbitrary. What I mean is that sample-to-sample variation in the sequencing depth does not reflect meaningful biological variation in the size or the scale of the underlying systems that are being measured. So for example, variation in sequencing depth does not correlate with microbial load in microbiome sequencing studies. Now, it's well known that this can confound inferences, and that's led to this kind of whole cottage industry of models and data normalizations that are aimed at trying to somehow overcome this limitation. Well, in reality, a lot of our recent work has been showing that really you can't overcome it. You cannot reconstruct information that isn't in the data, and these existing tools actually can lead to ridiculously high rates of false positives and false negatives, and I'll give a brief insight into that. But so to back up this statement, I need to actually introduce a little bit of terminology and introduce how we think about this data. I want you to think that the observed data, Y, is just an imperfect measurement of some underlying biological system. The underlying system, which we will denote with a W, represents the true as opposed to measured amounts of whatever we're trying to quantify. Again, the critical part is that we don't care about the data, we care about what the data can tell us about the underlying system. W can be thought of as a matrix with elements, the same dimension as Y. The elements represent the true as opposed to measured amounts. This means that we can also uniquely decompose that system in terms of its relative and absolute, or relative and totals. So WDN represents, for example, the absolute abundance of taxa D in the gut from which sample N was taken in a microbiome sequencing study. The parallel sign is going to denote proportional abundance, and the perpendicular sign denotes totals or scale. This is just saying that absolute amounts are equal to relative times total. The problem is that with sequence count data, because of this arbitrary sequencing depth, the data provides information about the composition, but not the scale. And this is why a lot of people call this data compositional, even though it's not, it's count data. Okay, so the problem that I really study is what happens when your research question depends on scale. So for example, when people do differential abundance and differential expression analysis, what they're really, one way of formulating this is as a problem of estimating log-fold changes, which I show, if I could reach, I'd highlight, it's the first equation in black up top. This is really on a log scale of difference in means. Taking the left equation, plugging it into the right, what we can show is that if I want to know how the abundance or expression of a particular taxa or gene D changes between conditions, theta D, I need to know how the relative abundance of that taxa changes between conditions, which is the theta parallel, and I need to know how the total microbial load changes between conditions as well. But the data only provides us with information about how the relative abundances change. Fundamentally, the data does not have enough information to answer this question. So I'm going very quickly, just to review some of the recent works that's been coming out of our lab. The first paper is a stat theory paper that really formulates this problem more formally in terms of the language of partially identified models. But let me just give the core conclusions. All normalizations that claim to overcome this issue, they don't. They are just making strong implicit assumptions about the system scale. You can't recreate information that isn't in the data. As a result, what happens is these methods can be incredibly sensitive to even slight errors in the underlying assumptions. leading to elevated rates of type 1 and type 2 errors that remarkably actually and provably will always increase as you get more data. You have statistical methods that get worse with more data. The solution is actually incredibly simple, though. We just need more honest statistical methods. We need methods that say information isn't in the data, we have to make an assumption, but we're going to also quantify uncertainty in the assumption itself. This leads to what we've started to call either stochastic normalizations or really scale simulation random variables, which use a scale model to explicitly make assumptions about scale and propagate that uncertainty into resultant calculations. The result is often remarkable decreases in type 1 and even type 2 error rates, in part because we can have more biologically meaningful assumptions. We just gave a workshop on some of these tools, highlighting how they've been incorporated into the ALDEX2 software package. Through a bunch of case studies, we have some pretty strong results. In short, we recommend these tools as opposed to the prior normalizations within ALDEX2 in all situations. They're universally better. Now, what I just described was a very quick overview. And I'm talking about tools that don't require that we make assumptions that few things are changing. Okay. However, in a number of situations, especially in microbiome data, people like to assume that few things are changing. If you actually believe, you don't want to just make the assumption, but you actually believe you're studying a system where few things are changing, we actually can create even more powerful tools. The first thing I can't review the full existing literature on sparse differential methods, but what I first want to point out is that there are some problems and pitfalls with the current literature. So increasingly, I'm seeing people propose penalized estimators, right? Estimating that most LFCs are 0. In particular, I'm seeing this pattern a lot. You have some model like a OLS estimator, and you add the following penalty. We say that at most K entities are changing in abundance between conditions. And then and I'm putting this in quotes, to account for the compositional nature of the data, they constrain this vector to sum to 0, essentially to be on a log scale, a simplical vector on a log scale. I just want to say this is nonsense. Let's just pretend that we are actually modeling a system where there are 5 microbes. I give a narrow spectrum antibiotic that kills one of them, such that this is the true vector of LFCs. This vector doesn't sum to 0. That model literally cannot even represent the truth if we gave it perfect data. In fact, if you try and analyze data from a simulation like this using a model that uses this penalization, what it's going to do is it's either going to say nothing's changing to maintain the sum constraint, or it's going to make the other 4 things have to increase and balance this -5. So essentially, I just want to point out, big pitfall. This is a really, really, big bad anti-pattern in modeling, but it is increasingly popular in the literature. So I want to take a step back and actually say there's actually some really simple solutions here. Let's just assume that we're modeling a sparse system, and it's sparse in the sense that the mode of the distribution of LFCs is equal to 0. This is a very weak assumption. Notice that this is not simply saying that more than 50% are unchanging. We're just saying that the largest cluster, the largest single value of LFCs is 0. That's what we're going to define as a sparse system. Now, using that equation from a few slides ago, what we can say is that the true log-fold changes are equal to the changes in the relative abundances, theta parallel, plus this constant term, which is the changes in scale, or for example, the changes in microbial load between conditions. In fact, using the mode line and using this system of equations, what we can say is that if we have a sparse system, we should expect that the mode of the log-fold changes of the relative abundances, the mode of the theta parallel distribution, is equal to the negative of the log-fold changes in the scale. This equation is what's essential for us operationalizing this and creating estimators that are more powerful when we're analyzing sparse systems. So I'm going to jump ahead a little bit This is what we call a scale model or a stochastic normalization. You can read some of our other papers to get a sense of how exactly this would be worked into an entire analysis pipeline. But for the moment, just assume that, I think fairly reasonably, given that the data provides information about the system composition, let's just assume we have a reasonable estimator for how the relative abundances are changing. We have a reasonable estimator for theta parallel. We apply to those estimates some strong statistical estimator of the mode, like a Chernoff or Ventnor mode estimator. And we set our estimate for how the scale is changing between conditions equal to the negative of that, with this additional error term that's kind of an honesty term that accounts for finite sample imprecision of the mode estimator and some other sources of potential error. This works with all possible, all of the larger toolkit of scale simulation random variables we've been developing. We can integrate it into ALDEX2. There's absolutely no perceivable increase in computational complexity. ALDEX2 is already very fast, and it's about as fast as you can get. Okay. Some simulated results I'm skipping over quickly. Basically, these are two simulations that don't come from our model. The second one in particular is just taken directly from Curtis Huttenhauer's Sparse DOSA model. And in both cases, we see that this sparse ALDEX2 based model has far better power and type 1 error control than the other methods. The other methods being the previous ALDEX2 or DSIG2. Sparse DOSA, notice that ALDEX2 actually has a type 1 error rate of about 98%, which is really, really, really bad. Okay. We actually have, while I haven't included them because they're hot off the press, we have similar results for real data and for larger simulations. Anyway, so very, very brief overview. The first paper there is the stat theory paper that goes over some of our impossibility proofs. For example, we proved that type 1 error control in general is impossible for differential expression, which flies in the face of a lot of published results. The second one is really written for more of a GenCompBio audience and outlines the changes to ALDEX2. The third one is on differential set enrichment analysis, a little different. But the stuff on sparsity is going to be, hopefully have a preprint out in a couple months. So bolded names, very important. Wang Gu is responsible for some of the recent work on sparsity. Thank you.
Thanks, Justin. We have time for probably one question as we switch slides.
Thank you.
Okay, I liked your example with the narrow spectrum antibiotic. And so I was considering if the bacteria are growing under some limited resource conditions, in fact, the other four would in fact increase. So, and as you correctly pointed out, the data can't actually tell you which of those two situations you're in. So what does your theory tell us in this situation? Could you give like an intuitive breakdown of what it would tell you?
So I don't think we have a theory in the sense of it's like we have a biological theory, but what I'd say is that let's say that you're modeling, if I understand correctly, let's say you're modeling in some limited resource setting.
Yeah.
And so you're saying, well, maybe there is a balance that occurs.
Right.
Maybe. So there might be some examples where this assumption that the log fold changes sum to 0 is exactly correct. I'd argue that it's pretty easy to show situations where that wouldn't be. So even in a resource limited setting, if you apply, let's say, a narrow spectrum antibiotic, there's probably a time window in which the balance hasn't been reached. And even if you are in a limited resource setting, it's probably unlikely that the balance is exact. So and if that assumption isn't exactly matched, that you'll still get type 1 error inflation.
I'm not advocating for a specific assumption. I'm just saying, like, what is the format of the correct answer? Is it that you return like a confidence range that includes 0, includes like both extremes? In the case where like the other 4 did increase, and in the case where it was actually a snapshot and they did increase. So is that what your tool returns, like the full confidence, like covering all possible
I see.
exchange?
So in this case, so if we're working in a sparse system, what our tool actually does, so under the assumption it's sparse, what our tool would recover is that that one is decreasing and the others aren't.
Why is that correct?
One was decreasing, the others aren't.
I'm saying, why is that I mean, that's also, why is that the correct answer?
I'm not sure. It's the correct answer because it's the way we've set up this like hypothetical simulation.
Okay.
Maybe we can talk offline.
Maybe we can
We
continue
can
on.
continue.